Let's get started. Welcome back. Unfortunately, I couldn't upload the lecture notes on time. I tried my best, but there is a very important deadline same time today. So and I couldn't do both at the same time. So, but it should be fine. Like, so we're going to have a live lecture, but the book is really good enough that like you can use that as a reference. I will release the scribbles from today so that it acts like a lecture. Okay, so if I say I'm going to write it after the lecture, I will not do it. So I will not make that promise. And a couple of announcements. Like, so first of all, the deadline for the project proposals is tonight. There were some questions in Piazza about not able to sign up. I don't understand why, because there is a Google form in Moodle where you can go sign up, right? So I think a lot of people thought they should go to the spreadsheet and edit directly. You cannot edit the spreadsheet. Spreadsheet is only there to show the registration so that in case you make mistakes, for example, a couple of teams emailed me saying, okay, so I made a mistake in the registration, so can you fix it, right? So it's for that purpose, okay? But if I don't have your project information in the spreadsheet by 10 p.m., we will not evaluate your project, okay? So because that acts as the list of projects. And we don't want uncertainties in this. Like, we don't want every week people coming and saying, okay, I forgot to register. So you should register, or you must register. And also you should upload your 1 or 2 page proposal in Gradescope. Again, in Gradescope, you have an option to form teams before submitting. So probably I should have given that link before, but I gave it in Piazza yesterday. So if you, a lot of you have figured out how to do that. I've done it already. But if you have not done that, so I have given a link for a help section on how to create teams in Gradescope in Piazza. So check that and form your teams, okay? So please form your teams. So what happens if only you submit a report without your teammates added is they will not see the evaluation, okay? So I don't think you can download the evaluations and show it to them because the evaluation is done on the top of the PDF, right? So for them to see the evaluation of both the proposal and the report, you should add them. And by adding them, automatically the mark gets copied to their grade sheet as well, okay? So it's important. And about the assignment 2, I think there was confusion in the date. I made it yesterday night 10 p.m., but TAs, when they opened the Gradescope, by default, they opened it for tonight 10 p.m. To avoid this confusion and to give you more time for the project proposal, I extended it to tomorrow 10 p.m. So you have 1 extra day, well, technically 2 extra days from the deadline that was given in the PDF, okay? So use that to submit your second assignment. Nevertheless, we will release this third assignment probably before the deadline because it is anyway due today, right? So we will release the third assignment soon. Now, some of you might be in my machine learning class, so I made this announcement already. So given that a lot of you are taking both the courses and you feel it is a bit heavy, so I decided to have a smaller third assignment, both the courses. A3 in ML is already released, like, and I think it is much smaller, much shorter than the other 2 assignments. Even for RL, like, so we're going to have a shorter third assignment so that you can spend more time in your project. Okay. Now, another quick reminder about the project. The project is a team of 3. Okay, so it means it's 3 people's time, not just 1 people, like 1 person's time. So treat it that way. Like, make sure all of you put efforts. Are there any questions? Yeah.
So first of all, about the Gradescope, I was looking, when I tried to submit, it said that the instructor should open the project as a team submission.
It is opened as a team submission.
Okay, so it was, as you said, it was after I tried. And
no, it was open from the beginning as team submission.
I tried yesterday, and first it was an error message.
But even in last week, there are 7 teams who have already submitted.
There's still can submit. There's a red box.
Oh yeah. So I think the message was about the outline, but you can still submit.
Okay.
Like, I did not put an outline for proposal because it is very difficult to give an outline for the proposal. But I have given a template outline now. So like there is just one question which says project proposal. So just tag all your papers with that one question. So that should help. Okay, so anything else in chat? No. Okay, and there was something. Oh, and by the way, we have a PyTorch tutorial today. Like if you are already following the schedule, there was also an email, I believe. So this tutorial is a joint tutorial for both the courses. So there will be some machine learning examples and like some reinforcement learning examples. But the point of the tutorial is to teach you how to use an automatic differentiation tool like PyTorch, so that for a lot of gradient methods that we are seeing in the class, you don't need to implement gradients by yourself. Like you just write the algorithm and you can compute the gradient automatically. Okay, so for example, let's say you're doing semi-gradient TD, right? So you want the gradient with respect to the TD error. Now you can just call dot grad or like whatever, like, and it is going to give you the gradient. Okay? Now PyTorch is one example. Like so, there is also TensorFlow, JAX, and there are a lot of other auto differentiation packages now. So probably PyTorch is the easiest, or it's my biased opinion. So we will just do PyTorch, okay? And for your third assignment, if you really want to spend more time, you can implement your gradients by yourself, but you are free to use PyTorch for the third assignment, okay? So, but we'll just stick to PyTorch, not any other auto differentiation packages because TS have to evaluate. So it is going to be much easier to implement, like, but it will be difficult if you don't attend the tutorial. So I highly encourage you to attend today's tutorial. If you have Flash, I believe some of you, for half of you, it is your lab time. For half of you, it is not your lab time. So if you have Flash, there will be recording available immediately after the tutorial, so you can watch the recording. And this tutorial is given by a research engineer from Facebook AI Research. Okay, so this is one of the researchers from Facebook who is actively contributing to the package itself. Like you will be learning from the experts. So I highly encourage you to attend it. Okay, so now let's get started after a lot of announcements. So today we are going to discuss about a new class of reinforcement learning algorithms, okay, so which is the idea of policy gradient methods. But before that, like as usual, a very quick overview of the types of algorithms that we have seen so far, right? Like so far, I think for almost the entire course so far, right? Like so, we focused too much on what I would call as action value methods or value-based methods. Okay, so what do I mean by action value methods? Like you take methods like Monte Carlo or TD or DP, right? Like so, we saw DP, and then we saw Monte Carlo, and we saw TD, right? Sorry, it's not TC, TD, right? So we saw these three classes of algorithms, like where like different algorithms had different flavors. Like so, for example, in the case of DP, like you need access to the transition dynamics, right? Like so, it's almost difficult in a lot of applications. In the case of Monte Carlo, like you were doing sample updates, like so you needed to go through the entire episode, which is possible with episodic, but not with continuing tasks, right? Like, and also the fact that you are using sample returns makes it slow learner and also high variant algorithm. We had discussed TD or temporal difference learning algorithms, like where it is like a one-step algorithm. Like so, instead of waiting for the entire episode to finish, you just make your updates right after one step, right? Like so, and we also discussed how to merge or combine MC and TD, which is n-step TD. Right now, the general recipe in almost all these algorithms is this idea of generalized policy iteration, like so where you had two components, right? So there was this value function that you were estimating, and like based on the value function, you had the policy defined, right? Like, so now, if you remember our discussion towards the end of the last lecture, I told you that value functions are not our goal, right? Like, so our goal is to act optimally, like always. Like the central goal in reinforcement learning is to act optimally, or in other words, find the optimal policy, like which is going to give you the highest possible return, right? Now, we were estimating value functions only as a mean to achieve this goal. Like, so you will estimate the values of each states or state actions, and then given a new state, like depending on like which value that you are estimating, like for example, if it is state action value, then you will consider all possible actions and pick the action which has the highest state action value, right? So basically your policy is constructed based on the value function, right? Now, it has some challenges, like for example, like when you do function approximation with value-based methods, the policy improvement theorem doesn't hold anymore, right? So basically, like you are in a situation where you're doing some approximations, you're not sure if you're going to get the best results, right? Now, today, we are going to see a second class of reinforcement learning algorithms, okay, so which we're going to call as policy gradient methods. Okay, where the idea is to forget about value functions, okay, like and directly approximate the optimal policy. Okay, so or in other words, instead of parametrizing or coming up with a function approximator for value functions, can I come up with a function approximator for the policy itself? Okay. Now, the most attracting reason why we should do this is, as we will discuss in the first half of the lecture, there is this theorem called policy gradient theorem, okay, so which is going to guarantee us that we will reach a good policy by approximating the policy with, by doing function approximation with policy. Okay. On the other hand, we don't have such guarantees with function approximation with value-based methods. Is that clear? Okay, so now let's talk about policy gradient methods. Now, if you remember, like when we did function approximation with value-based methods, like for example, let's say I'm doing state value. So I was doing V of S given some parameter W, right? So this W was the parameter of the function approximator, right? So similarly, like we are going to parameterize our policy now. So just to avoid confusion, like we are going to call our policy parameters as theta, okay? So I have my policy pi, which is going to give me the probability of picking an action A given yes, okay? And it is parameterized by theta. Is that clear? Now, this is equal to the probability that action is equal to A, given state is equal to yes, and my theta, t is equal to theta. Is that clear? Now, as we will see today, like so, some policy gradient methods can also estimate value. Okay, in which case, like you're going to have theta, which is the parameter for the policy approximator. Okay, and we can also have W, which is the parameter for the value function approximator. Is that clear? Okay, now we have the model, like, or at least a rough outline of the model, like, which is basically you're going to take some state yes, right? And I have this function approximator. Okay, now this function approximator could be a linear model, like in which case it is basically theta transpose x, right? Or as we have seen in the previous lecture, it could even be a neural network, like so. So you have some function approximator, okay, with some parameter theta. Okay, now this theta could be the weights of a linear model, or it could be just the weights of the neural network. Okay, so you could use any any complex function approximator that you want. Okay, now like whatever the function approximator is, like so the only requirement is this function approximator has to be differentiable. So I should be able to get gradients from this function approximator, and this is going to give me phi of yes given pi of a given s theta. Is that clear? Now this is my model. Now to train any model, like we need some objective, right? Now what could be an objective? Okay, so in the case of value function approximator, the objective was just the error in value prediction, right? So for example, in the case of semi-gradient TD, like so you were trying to minimize the TD error, right? Now, what could be the objective for a policy function approximator? Any idea? Sorry?
Minimize the regret.
Okay, so minimize the regret. Okay, so regret is often an incomputer, like difficult to compute, right? Like we don't know the optimal policy. So an equivalent of that is to maximize the return, right? So in fact, isn't that what we care about, like in this reinforcement learning problem? We want to maximize the return, right? Now, we are going to call our performance measure. We want to maximize some performance, okay? So in this case, it happens to be maximizing the return. So let us just call our performance measure as J of theta. Okay, now this performance measure could be anything that you want to maximize, but for the purpose of our discussion today, like so we are going to consider this to be the value of the first state. Okay, if you think about it, so what is the value of the first state? It is the maximum return. Like it is the return, actual return that you get from the episode, right? So if you can maximize the value of the first state, it means you have figured out a policy which is going to give you maximum return. Is that right? So we are going to call our J of theta to be V pi of, so I'm going to put theta here, like to note that this pi is parameterized by theta. So V pi theta of S0. Okay, so where S0 is my first state. Is that clear?
But often we stop at a point where, I mean, what is important for a policy is, to get a policy is we just need to see the maximum of the values near it, right? Like, so if you just know which state to go next, that idea if you get, we stop at that point in generalized policy iteration also.
Yes, but there's a difference here, right? So we are not estimating value. Okay, first of all, we are not estimating value at all. Okay, so we are like, there is no value function estimator here. Like, so we are doing function, like we are doing function approximation, but for policy. Okay, so then how do I compute this value? Like, and how do I take gradient with respect to value? It's a bit complicated. We are going to see that in yeah.
You can just take the return.
Yes. So we can approximate this with the return. Yeah. Okay, we are going to see like how to make this more tractable. Like, but for the moment, let us just assume that, well, it's not assumption. Like, in fact, this is the true goal, right? Like, so this is what we care about. Now, how to do it practically, we will come to that. Okay. But before that, right? Like, so we still have some more discussions here. So now, if I have some performance measure J of theta, okay, our goal is to maximize the performance. Right? So now, in the case of value function approximation, our goal was to minimize the TD error. So here we want to maximize the performance. So we are going to do gradient ascent instead of gradient descent. Okay. So we are going to update the parameter theta, t plus 1 is equal to theta t plus alpha times, okay, the gradient of theta t. this performance measure. Okay. Now, instead of computing this exact gradient with respect to j theta, we are going to do a lot of approximations. Okay. So specifically, we will do some stochastic approximation. So the hat just means that it's a stochastic approximation of this actual measure. Is that clear? Now, any method which updates its parameter, the policy parameter, using this kind of form, functional form, we are going to call that as policy gradient methods. Okay. Now, we will also discuss another class of methods today, which is the idea of acrocritic methods. Okay. So where the actor is your policy network or policy function approximator, okay, and the critic is a value function approximator. Okay. So when you use both policy and value functions together, okay, so we are going to call that as acrocritic methods. Is that clear? But first, let's talk about the vanilla policy gradient, like before we jump to something which combines both policy gradient and value functions. Okay. Now, let's talk about the advantages of policy gradient methods. Well, I told you that the one attractive advantage is like there is policy gradient theorem. So like we are going to have some guarantees about the policies that you are learning, like which is not possible for function approximation with value-based methods, right? Like, but there are many other advantages for doing this. Okay. Now, so before we begin this, like, so have we seen anything like this before in the course?
In bandits, we had a stochastic.
So in bandits, we have gradient bandits, right? Like in fact, that was like a precursor to whatever we are going to discuss today. Okay, so if you think about gradient bandits, in the case of gradient bandits, like we were not estimating the values of the actions. We were actually estimating some preference function for actions, and then we took a softmax over the preference function, right? Like so, now we are going to do the same thing here, but instead of action, in that case there was only one state. Here we have many states, right? Like so we are going to have some numerical preference. Okay. Now the preference, the H function is given as state action given theta. For every state action pair, I'm going to construct, like I'm going to estimate a preference function. Okay. So the higher the preference for an action, the larger the probability for sampling that action or using that action. Okay. Now we can set up a probability distribution over action. So pi of A given S theta, okay, which is basically a softmax over these preferences. Okay. So it is e power h of S A theta divided by summation over B e power h of S B theta. Is that clear? So this is basically a softmax function. So it's a softmax in action preferences. Okay. Now, these action preferences can be like the theta of action preferences could be anything. It could be a linear model, or it could be a neural network, or it could be any other complex parameterized function approximator that you can think of. Okay. Now, to make our discussions simpler, we are going to go with linear function approximator, but we will also see how to extend this to neural networks towards the end of the lecture. Okay. Now, for now, let us just assume that my h of SA given theta is simply theta transpose x of S comma A. Okay, where this x of S comma A is the feature vector for state. Yes. Okay. Now, these feature vectors, like you can construct it as using any of the methods that we have seen so far. Like so, you could use polynomial features, or you could use style coding, coarse coding. or you can come up with your handcrafted features. Okay, so this is the simplest possible model, and we will stick to this for our discussion. Is that clear? Okay. Now, what are the advantages of taking this alternate approach instead of using the value-based methods, right? Like, so now there are several advantages. Like, so the first advantage is that the approximate policy that we are learning, right? We can actually approach a deterministic policy. Okay, so we are learning a stochastic policy, right? But this stochastic policy that we are learning can approach deterministic policy if needed. Okay, so for example, let's say I am in an environment, like it would be a simple grid world. Okay, let's take the simple grid worlds that we have seen so far, right? So when you do epsilon greedy with these simple grid worlds, so the best policy that you could converge to is some epsilon soft policy, right? So, or in other words, even if you have figured out what is the optimal policy, like you will be always like with epsilon probability, pick a random action, right? On the other hand, like, so if you use a policy function approximator, okay, now these action preferences are continuously updated. So for example, let's say that in one particular state, there is only one action, which is the highest possible, which has highest possible return, okay? It is clearly the winner. So then in theory, the preference for this action could go to infinity, which means all the other actions will have almost zero probability, okay? Or in other words, the softmax function could peak, like so. Let's say there are 3 actions, right? So now this function that you see here, like so, it could become something like 0.999, 0.0001, if first action seems to be the best action, okay? However, this is not possible, or at least it is not straightforward to do with value function based methods, okay? Now, there are some ways to do this. Like, so for example, like what if I construct my policy as a softmax over the action values? Any idea? Just like how I'm constructing my policy as a softmax over preferences, right? Like, so I can also take my final action values for all the states in my DQM and put a softmax over it, right? Now, does that going to solve this issue? Like, is it going to be similar to what we can achieve here? Any answers in the chat? In the class? So what I'm proposing is, like, you take the value function, like let's say q of s comma a for different states, right? Now you put a softmax on top of that. And now this is your policy. Can that give you the deterministic policy that we are looking for? Or in other words, like would that softmax converge to something like this?
The difference between values might be very less sometimes.
Yeah, so it depends on the values, right? Like, so there's nothing in the value function based value method that tells that it should peak, right? So like, for example, if truly it is going to converge to the true values no matter what, right? So now the true values for 3 states might be in such a way that the first state is 10, second is 8, and the third is 2. Now this is going to have some probability distribution where there is high probability for the first, but there's also a significant probability for the second action, right? So you will never converge to the kind of sharp deterministic policies that policy gradient can converge to if you use that approximation, okay? However, one can use temperature parameter in the softmax, like you can add a temperature here, like which helps you to peak the softmax. But then how to tune this temperature is a big question, right? So in general, it is very difficult to come up with deterministic policies, like if needed by using value-based methods. On the other hand, it is going to be much easier to do that with policy-based methods. Is that clear? Yeah?
So why is it difficult with value-based method? I mean, like, why don't you just pick the x which has the highest Q value? Like, that's your deterministic policy.
Yes, you can do that. It's an approximation. But imagine there is no separate training and testing, which is often the case in reinforcement learning, right? Like you're acting out in the world. So if you start being greedy, then like you are moving away from whatever algorithm that you were following, right? Like so almost all the algorithms we have seen so far like was using epsilon greedy. There was only one algorithm which was able to learn deterministic policy. Can someone remind me what was that algorithm? We have seen one algorithm in value-based methods which can actually learn the optimal deterministic policy. No.
Value.
No, I'm talking about learning-based methods. So do you remember Monte Carlo with exploring starts? Right? So when you do exploring starts, which is a very unrealistic assumption, then you can actually learn deterministic policies, right? Like so this is the first advantage. Okay. Now the second advantage is policy-based methods, right? So with softmax can actually enable okay, so the second advantage is like it can enable the selection of actions with arbitrary policies. Okay, so what do I mean by that? So in a lot of applications, the policy has to be truly stochastic. Okay, like, or in other words, like, so there is, like, the first advantage was the deterministic case. Okay, now I'm going to argue that even in stochastic case, policy approximators are better because there might be some problems like where, like for some action, like for some state, you might have like two actions which has almost equal probability, like or slightly above and below probability. Okay, so for example, the book gives some example from poker. Okay, so like for example, in games like poker, right, like so, which is a card game with imperfect information. So the optimal play often is to do two different things with specific probabilities. Like so, for example, when you're bluffing in poker, okay, there may be two things that you can do, like and you have to take them with like equal or almost equal probabilities, like if you want to be stochastic to the other opponent, right? So now these kind of policies are very difficult to learn, like with epsilon greedy, because the problem with epsilon greedy is you always learn one action which has highest probability, and there's only epsilon probability for other actions, right? So there is actually an example to illustrate this advantage. Okay, so let me go here. So here you see simple. So this is the world that we are going to consider. Okay, it's a simple four-state world. Okay, there are only four states. So there are three non-terminal states and one terminal state. Okay, now there are two possible actions. You go either right or left. Okay, now in the first state and in the third state, you take right, you will go right. You take left, you will go left. Okay. However, there is this confusing second state where you take right, you're going to go left, and you take left, you're going to go right. Clear? Now, the reward is -1 all the time until you reach the goal state. Okay, so reward here is going to be -1 all the time until you reach the goal. Okay. Now, imagine I have a function approximator, okay, which basically treats all these states as same state. Okay. Now, it might look like a very specific example, but it is kind of possible because when you do function approximation, there are a lot of mistakes and loss, right? Like so, like sometimes the function approximator cannot differentiate two different states. Okay. Now, in this case, I'm going to explicitly construct this function approximator. Okay. Now, x of s comma right for all the states is going to be just 1, 0. It's a two-dimensional feature vector. Okay. Whenever I take right action in any state, my function approximator is going to tell me like take 1, 0 as the feature. Okay. Now, similarly, x of s left is going to be 0, 1. Okay. Now, what happens if I do epsilon greedy here, right? So now if I do epsilon greedy, okay, I can only converge to one option, either to the left or to the right, right? If I converge to the left, then with epsilon by 2 probability, I will take the right once in a while. If I converge to the right, then I will take with epsilon by 2 probability left once in a while, right? Now, here you see that with epsilon greedy of left, this is the value of the first state. Okay, so in other words, you are able to achieve -80. Okay, it's because it is always trying to go to left, right? So to go to right, like you need this epsilon by 2 probability to go right, yeah?
So when we use epsilon greedy, it's on the features, not on the states, right?
Yes. Okay. Yeah. It's a with function approximation. Okay. Now, the other option is to do epsilon greedy with right? So your algorithm could converge to either of the solutions. Now, if you converge to epsilon greedy with right, it seems to be better than the left, but it is still not the optimal. Like you get approximately -44. Okay, so the epsilon greedy right is getting -82, and this is getting -44. Okay, so however, if you do policy gradient, okay, policy gradient can actually find the best probability, okay, for taking right, okay, so which is in this case happens to be 0.59. If you have a probability of 0.59 for right, then you achieve this optimal return or value, which is -11.6. Is that clear? This is actually really simple, like for policy gradient. On the other hand, it is almost impossible for value-based methods. Is that clear? Okay. Now, this is the second advantage, like situations where you need stochastic policies, like with good amount of stochasticity, policy gradients are going to be better than value-based methods. Now, the third advantage we have is sometimes, okay, policy may be simpler to approximate. Than value. Is it clear? So now, of course, in some situations, maybe action values are simpler to approximate. Now, depending on what is your application, like depending on what the nature of your application, like you can pick either policy gradient approach or value-based approach. Okay, so now in situations where policy is easy to approximate, policy gradients are going to learn much faster than value-based methods, and like you get better performance. Okay. On the other hand, like of course, like if value functions are easier to estimate, then probably it's a better idea to go with value-based methods. Okay. Now, finally, the another advantage that the policy methods have is like, so this policy parameterization, right, is sometimes a good way of injecting prior knowledge. Okay, so this is a very important advantage because now, for example, let's say I have some prior knowledge about what are good actions and like what are critical states and so on, right? So I can inject these prior knowledge to the policy function approximator, at least as an initialization, as an example. One example is through initialization. You can also inject it in other forms, like so now. So this is easier or much more intuitive, like than having some prior knowledge about value of the state, right? Like so, how can you think about value of a state, right? Like on the other hand, like thinking about actions might be easier. So this is another advantage. Is that clear? Okay, I think I sold policy gradient methods too much. So now, before we see some example algorithms, like in policy gradient, like let's talk about the policy gradient theorem. Okay. Now, so the thing with value-based methods is like we often do epsilon greedy on the top of value-based methods. And this policy of the value-based method, right, it changes abruptly. Like, for example, you sample some state action, you update the value of that particular state action, okay? Like, let's say there are 4 actions, A1, A2, 3, A4. Now, let's say based on my current estimate, this action is having the highest value, okay? Now, this action is going to have 0.99, let's say, probability, and the rest has some simple epsilon by 3 approximate, 0.99 plus epsilon by 3. I'm setting epsilon is equal to 0.01. Okay, so if you have epsilon is equal to 0.01, then probably this is right. So now, let's say based on a couple of experience, like value of this particular state increased, and it's higher than A1. Okay. Now, my probability of taking actions is going to shift abruptly to the second action. Now, this action is going to have 0.99 plus epsilon by 3. This action, which had almost 1 probability, now just have epsilon by 3 probability, right? So in some sense, like there is significant shifts in the policies, like whenever like I make updates to the value function, right? On the other hand, so the nice thing about policy gradient methods is we are computing gradients with respect to the policy itself, right? And we are making small changes. So we are going to move continuously over the space of policies. Okay. Now, it is really like we are working in 2 different spaces. So in the case of value-based methods, like we were working in the value function space, right? We were moving in value function space. Now, every small change in the value function space can actually be a big step in the policy space, right? On the other hand, with policy gradient methods, we are actually moving in the policy space. Okay, so you will be moving in a smoother way. Now, this fact that you are moving smoothly, like continuously in the policy space, right? Like so, it helps us to come up with stronger convergence guarantees for this class of approaches. Okay. Now, this is dependent on the fact that there is continuity in policy. Okay, so now that is going to give us convergence proofs. Well, of course, we will not do convergence proofs for algorithms in this course. Nevertheless, we will discuss and derive the policy gradient theorem because it is very important. Okay, now I don't want to start and not finish. So we have only 3 minutes for break. So probably I will just stop here and we can take, yeah.
Should all of those be epsilon by 4?
Oh yeah, that's why I said it could be. So, okay, yeah, that's right. Okay, so I'll just remind you what is J and then like we will stop so that there is continuity in discussing the theorem. Okay, so now the performance that we are considering here is basically V pi theta of S0. Okay, but S0 is the start state of the episode. Is that clear? So probably we'll take a break now and start at 10:30. It's okay to have extra payment, so it gives me time to prepare. So we will continue at 10:30. Okay, just for today, I will take your questions after the